Okay, guys, so this is the continuation of the last lesson. So here's an example to go along with that idea. And again, remember we're talking about using this cosine value to find the angle between two vectors. So if we find the angle between any two vectors here, and I've got one more vector up there than I need, but that's okay. So I've got four vectors listed, and if you take a look here, the first project we're going to look at, first problem is A. So if we add vector, if not add, sorry, if we find the angle between these two vectors right here, u and v. So what we're going to do then is use that cosine formula of u times v, that dot product, divided by the magnitude of the two vectors. So u times v, so if we do that dot product, we're going to get the following sum. If you finish that out, obviously you see that you get negative 8. The magnitude of u is radical 14. The magnitude of v is radical 20. So that would simplify down to a negative 4 over radical 70. Now, when you take a look at this, and that's all the way reduced, okay? When you take a look at this, what you notice is it's negative. Well, if it's negative, then that means it's less than 0. So if it's less than 0, in other words, if that movement, that product between those two vectors is less than 0, that means theta has to be in between pi and pi over 2. So between pi and pi over 2, when we do the inverse cosine of this angle then, that means the value that we're going to get is 2.069 radians. So you just want to make sure that's the number that you're getting when you do this, okay? All right, now let's take a look at the next one. U and V, or U and W, excuse me, right here. So again, the dot product of those two vectors. Oh, look at that, it ends up being 0. I love 0. It's nice. Distance formula again, or in other words, the magnitude of u is 14, radical 14. Magnitude of w is radical 6. That gives us something on the bottom that is totally irrelevant since the numerator is 0. So if that product of those two vectors is 0, where does the cosine of theta equal 0 at? Well, it equals 0 at pi over 2. So theta is pi over 2. Okay? Now, there's an alternate form of dot product, also using this kind of concept here. If you think about it, what are we dividing by? Well, we're dividing by the magnitude of these two. But what I could also do is the following. I could find uv by moving this over here, right? So I can just manipulate this in any way that I want. So let's take a look at that real quick. Because if I know theta, then I can just do it differently. So using that exact same formula, u times v equals the magnitude of u times the magnitude of v cosine theta. All right? So if I've got an example where I know that the magnitude of u is 10, the magnitude of v is 7, and theta is, let's make it something nice. How about pi over 4 is not real nice. It's okay. Pi over 4, then I could find uv by just multiplying all that together. So 10 times 7 times cosine of pi over 4, that's 70 times, and then what's the cosine of pi over 4? Again, that's 45 degrees, so radical 2 over 2. I can simplify the 2 and the 70. So 35 radical 2, that is the equivalent to that multiplication. Okay? So there's another form there of the dot product. So now, there is also a process where you can take a look at these in thinking about them being the law of cosines. Okay, so we've kind of been doing that a little bit, but there are a couple of pieces that I want you to notice. One is the following. Make sure you pay attention to this, because if theta equals 0 or pi, then we've got parallel vectors. I'm going to put little arrows on these because they look so much like similar symbols that we've got in this vector notation. And if theta is pi over 2, that's 90 degrees, remember? Then we've got orthogonal vectors. So that's a way that you can test to determine if two vectors are parallel or are perpendicular to each other, is just to verify that piece. So if you know that to be true, then automatically you know those two things to be true. Okay? So likewise, backwards, right? So if they are perpendicular, then you know theta has to be this. If they are parallel, you know one of these two things has to happen. So in continuing that thought, let's just kind of illustrate this. Let's say that we've got two vectors, W and V. Well, if I take that magnitude of V times the magnitude of W times the cosine of pi over 2, well, cosine of pi over 2 is 0. 0 times anything is 0. V times W is 0. All right, so what that tells us then is the dot product is 0. Right here, they have to be perpendicular. Okay, so it works backwards. If dot product is 0, then they're perpendicular. They're orthogonal. Okay? Alrighty, so I've got a couple more pages here. We'll see if we can get through. A couple of extra notes. Do keep in mind that I, J, and K are all also going to be mutually orthogonal to each other. The reason why is because when you do those dot products, you're going to get 0 for everything. I has a 1 in the first place, but then J has a 1 in the second location, K has a 1 in the third location. So every location in that vector notation, you're taking times 0. So everything is going to end up being 0. So the dot product of all three items is 0. Okay, so that's a note. I'm not going to take the time to write up here, but you should write that down. Those standard unit vectors of I, J, K, the dot product of those is 0. So if you've got a vector in 3D space, then you'll notice that it creates an angle with all three axes, right? In other words, all three standard unit vectors. Because if I've got this angle that's going like this direction, then it's making an angle here. Here's my arm here. It's making an angle here. It's making an angle here. And it's making an angle here. Okay? So, with that in mind, those angles created with 3D axes in space by vectors are called direction. That's awful. Sorry. Direction angles. Okay? And alpha refers to the angle formed by the vector and I. Beta refers to the angle formed by the vector and J. And gamma refers to the angle formed by the vector and K. So here's how you find those. You simply substitute those values in that cosine function, okay? So cosine of alpha equals your vector 1 combo with the magnitude. Cosine of beta would be the second. And cosine of gamma would be your third. All right? So I'm going to give you a second here, and we'll do an example. Let's find the direction angles for the following vector. So you may want to pause and write this down. I'm going to erase this. Find the direction angles for V equals 2I plus 3J plus 4K. All right, so let's first get that magnitude. So we've got the square root of 4 plus 9 plus 16. I wish that came out nice, but it doesn't. Again, it's radical 29. So then the cosine of alpha is, now alpha, remember, is the angle that you get when you are intersecting with I. So all you do is you take your coefficient for I that you see here, okay? So 2 over radical 29. So you do the inverse cosine of 2 over radical 29, and you should get 68.2. And that's in degrees, okay? Cosine of beta, 3 over radical 29, and that will give you 56.1. And then the cosine of gamma, 4 over radical 29. So when you do that, you would get 42 degrees. Okay? So vectors that are parallel can also be proven to be parallel if you can manipulate them by some scalar to get them equal to each other. So let's say, for example, that you have got a vector, two vectors, let's say, that look very similar to each other. What you notice is that these values here are either multiples or factors of values in the other vector. If you can multiply one of your vectors by some scalar number to get the other vector, then they're parallel to each other. It's like saying slope. Remember, two lines have the same slope if, or they're parallel if they have the same slope. Sorry, lost my train of thought there. Well, when you're doing these, if your coefficients can be made to be equivalent to each other, then those vectors are going to be parallel. Okay? It hasn't told me I'm running out of time yet, so I'm going to go ahead and show you this one. So, let's say we've got A, which is 2I minus J plus 3K, and I've got B, that is 2/3 I minus 1/3 J plus K. Well, what happens to this if you take 3 times all these components? You're going to get, you take that by subscalar 3, you're going to get 2I minus J plus 3K, which is this. That means that they are parallel. Okay? All right, that's what I've got so far for today. So take a look at those things. You can follow some of the examples in your book, but that kind of gets us through most of section 3. There's some application that we need to try and do, but I haven't gotten that far yet. So if you can get these 2 videos watched and understood, we're good. Thanks.